Hey everybody, this is Larry. This is day 24th of the April Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem, critical connections in a network. Now I'll let you know what I think about this problem, if this is the problem that I think I am, or it is. But yeah, I usually solve these live, so it's a little bit slow, fast forward. But for this one, it is a connection that removes will make so I was wondering whether, because it looks like there's a critical path and you have to try to figure out what critical paths there are, which is of course in graph theory is just called bridge finding. And and this n is going to be 10 to the fifth. So the naive way of doing it, where you try removing every edge and seeing whether the graph is still connected, well, that's not going to work. So basically, this is bridge finding, and to be honest, I don't feel like it is going to be on, or like it's one of those things that are just such a trivia type problem that if you don't know it, it's probably okay to not learn it, because at least if your goal is for interviews. For competitive programming, it still comes up from time to time, but it's actually not that common either, in either case. But yeah, so you need to Google something. I would Google something like find a bridge in a graph. Um, I, I do know how to solve this in linear time, but I'm not going to go over this algorithm too deeply, because there's a lot of literature out there. This is a relatively I mean, it's not standard. It's just that this is standard is the wrong word, because but it is one of those graph theory problems that allow that people teach in textbooks and stuff like that. And as such, a lot of people know it, but it's also like people know it because they were taught. You could maybe figure it out if you're really strong in using depth first search and having a couple of observations, but these observations I just remember, so I could kind of go from scratch. But yeah, oh yeah, and this is not even a hint. This is just using Tarjan's algorithm, and I was just curious what hint they could give you. That's just finding a bridge, and of course, similar to what I was saying, if an algorithm has someone's name on it, it's probable that it's okay that you didn't come up with it, I think. So this is kind of almost like a useless interview problem as a result. Or like you can learn it, but it doesn't. I don't really think it comes up that often on interviews, but I could be wrong. So I would study things that are more that would come up more commonly, unless you really ran out of things to study for. But yeah, but the idea behind excuse me, I have allergies, so like my throat is a little bit itchy. But yeah, but the idea behind this is just it's just this idea of back edges, and I'm hand wavy a little bit, as I said. Try to find like, because this is such a topic that people have discussed, that you can probably Google it and it'll give you a good enough literature on it. So I don't feel like I'm going to go that deeply into it. But the general idea, and this is going to be hand wavy, is just that if you draw a graph, and you do a depth first search, you kind of want a depth first search tree. A path is critical if you think about it from in a perspective of a depth first search tree. A path is critical if there's no way to go to a point before that path exists. So basically, if you do a recursion and you go lower on the recursion stack, there's no way for there's no edges from a lower node to an earlier node. So that's kind of the general idea, and then you kind of from that idea, there's a lot of bookkeeping. So let's get started. You can also Google this algorithm, because, like I said, you're probably not going to figure it out. For me, I have this idea, so I might not implement it correctly because it doesn't come up that much. So I might just mess up. But you can watch me, try to implement something that I know the algorithm of live, and then see what happens, right? So yeah, so edges is equal to. I like to put things in an adjacency list. So yeah, so connection is just A and B, right? Okay. Okay. And now we have to set up a few things. I don't. Mm, yeah, I think. Okay. This timer. I never know when these are keywords as well. So parents for each node. Yep. I don't know if this is necessary. It's been a while. I like to make this an uppercase N, just for consistent with my other code in general. First visited, something like that. Yeah, maybe I could roll that into. Yeah, I'll try. I'll go for readability. I generally okay. Let's actually use this, and then the lowest point that it can visit is also this, I think, and yeah. And then, so I think those are vaguely the idea of setting up, and then we just do for x in range of n. Is this from just seeing if this is one index or zero index or zero index? I guess that we need to answer array. Okay. And then now it's a little bit messier. So okay, so let's just say was it true? So yeah, so then first visited of current is equal to t, maybe t1, and then the lowest that we can visit is also t. No, is it t or node? Nope. Yeah, okay. And then now for x in edges of current, if not visited of x, compile the first search x. But before that, we want to set the parent of x is equal to current. Okay. And then now we have to look back, and I messed this up enough times to know that I always have to say this part out loud. So the lowest. So I think I've been just kind of thinking about this too much. But yeah. But so far, what I've done is that okay, for each node, I was focusing on thinking about this part. That's why I haven't talked about this. I usually am more talkative about it. But yeah, for here is just say for every, we go from every node, and if we haven't visited this node yet, we do that for search. In this case, I think this is a connected graph, so I think you only need to do this once. But in theory, if you have a forest or something like that, then maybe you can, that's just my general pattern. And here, we mark it as visited so that we don't visit it again. And this is the time that it is first visited, and this is the lowest that it can be visited. Meaning that this is the earliest pass that it can get to. and this is just setting up the parents. Do I need the parents? Always forget if I need the parents. Yeah, I think we do actually. Okay, and then now the lowest of current is equal to the lowest that the depth first search can go. So it's just and then lowest of x. That's basically this is saying we update the lowest on the. If you think about the recursion tree, the earliest time that an edge that is connected to this edge can go. Yeah. So else, so if this place is already visited, and the parent of x is not equal to current, meaning that if we already visit this place, or the other way around. So, no, yeah. If x is not equal to, so we already visited, and this is not literally like the back edge, like literally the parent. Then we do something similar where then yeah, we set that equal to the first visited of current. Or did I mix it up? No, I mixed it up. Yeah, okay. Yeah, basically this is saying that if the edge that we're looking at we already visited, and it is not literally the one that is like we just visited, then that means that it went above the edge that we visited, and then we want to see what is the time we visit that area, and that we set the lowest current here. And then here, now we just do if the lowest of x is greater than the first visited of current, then we want to add this edge as the answer, right? X and current, I guess. Because basically this is saying that, okay, we look for all the we have this recursion tree. We went for all the things that it can possibly visit, and all the things that it could possibly visit, we cannot get to a node that we visited earlier. And in that case, that means that this edge going from the current node to the X node, meaning that this edge, if we remove it, then everything will be contained, and therefore, it would separate the two graph, right? That's basically the idea. I think that's roughly it. I think I have to set some non-local on T actually, but I think this is mostly it. Yeah, let's give it a try. Usually I test a little bit more while I'm coding it, but obviously this is now wrong. I'm just trying to look at other examples, but okay. I mix these up. Oh, this is the lowest of that's it. Like I said, I usually mess up one of these, so I'm trying to figure out did I mess it up here? So okay, and did I actually visit? Do I have to? Yeah, that seems okay. Yeah, this seems okay. So what did I do wrong? Let's print out current real quick. Did I set up the edges correctly? Yeah, it should be okay. So okay, so we do visit everything. So if we haven't seen x yet, we set the parent of x is in current. Yep. We do a depth first search of x. Sounds reasonable. And then now we check whether the lowest of the current node, and then we set it to the lowest of the x because that should be updated with whatever recursively. And if, oh, is this right? Oh yeah, okay. I think this is right. That's odd. Okay, let's take a look. So 1, 3, so where do we go first? We went 0, 1, 2, 1, and then 2, and then 1 should go to the 3, right? Okay, so this is not even getting here. Does this go through at all? Did I mess something up? Oh, I am dumb. Whoops. Huh. I'm so used to these. I don't know how that still mostly worked, but okay, fine. Okay, so that's good. Just a little silly mistake. I was wondering, I looked at that code and I keep on saying like it just looked okay, but in a weird, confusing way. But yeah, so this looks good. Yeah, there probably maybe some edge cases. Let's try. Let's try at least one of them. Let's just do 2. Okay, looks okay. Let's just give it a submit, mostly because for time's sake. May test a little bit more intensely if I wasn't. Okay, cool. I was worried for a second that I might get time limited, but this is linear time, as I'll go through in a second. So yeah. So what is the time complexity of this, right? Well, this is going to be called n times, where n is the number of vertices, and for each edge we will go, each edge each edge that we're given, it will correspond to one. Well, I guess technically 2, but over one number of edges in edges, and for each of those edges we only visit it once, right? So this is going to be linear time in in the size of the input, which is O of v plus e, where v is the vertices, and and e is the number of edges. So, and in terms of space, as we mentioned, well, this is going to be O of e. So yeah, so that's going to dominate, and all these are O of v, where v is n, which is the number of vertices. So we get linear time, linear space, and that is, I believe that's Tarjan's algorithm. I actually don't remember that. I just remember, for me to remember, it's just to remember the invariant of this problem and the observations that that what I said about the tree. As I mentioned before, I'm not going to go into that deeply just because this is a well-known algorithm, so there are probably a lot of literature about it, and I am a little bit lazy to kind of, or like what I'm going to, if I were to explain off my head, it's probably not going to be complete because, that's just the way it is. Because I didn't do any research about this. It's just me solving this live, right? But yeah, the other one that you might kind of see that is similar, just to kind of give you another thing, is called articulation point in a graph, and that's the one that is, instead of finding an edge, you find a node that and you have a similar algorithm here to this one where instead of an edge, you look at the node, and that node will allow, it's just a different if statement essentially. I believe that is the case. I have to think about it again. But the concept is still that you have these depth first search trees, and then you want to, a point, a vertex is an articulation point if you cannot reach to a node that you have visited before that, which is connected the graph into 2 different ways. But yeah, Yeah, I think that's all I have. I think, yeah. Maybe I could explain this part a little bit more, but I think that's all I have. Let me know what you think. Hit the like button, the subscribe button, join me on Discord. Like I said, I don't really value this one that much for an interview. Um, but here it goes. So yeah, take care of yourself. Good luck on the weekends for the contest and stuff. But enjoy your weekend. Hope you have a great weekend, and I will see y'all later. Bye bye.